Hello, Dr. Keith Schubert here. This is Questions from Digital Logic 2337. One of the questions on feedback was why the fractions and looking at the prime factorizations. Why does that work for telling whether something terminates or not? Consider for a sec something that doesn't terminate. Like we mentioned 1/3 in class. 1/3 is equal to, if I put it into a decimal representation, 0.333, repeat on. Well, the first digit here, this is 3/10. The second one, that's 3/100. So I add those two together, plus 3/1000, plus, and it keeps going, 3/10,000, so on and so forth. I'm just going to put dot, 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 because it keeps being 3 over the next power of 10. Well, this is, each of these are powers of 10. That's 10 to the first, 10 to the second, 10 to the third. Now, if this were to terminate, now it obviously doesn't, but if I had a number that did terminate, that means it would be able to be expressed as some number a over 10 to the first plus b over 10 to the second plus dot, dot, dot. All right? Out to whatever, some r or something over 10 to, whatever that, however many digits out I am, right? 10 to the j or whatever however many digits down that is. Right? So in any case, it would have to be expressed as a finite number of these. So that would mean when I'm calculating my fraction, it has to expand out. Does that make sense? Okay. When I'm looking at this, I'm expressing this division by 3. So that means I have to be able to take this 1/3 and multiply top and bottom by something that's going to be able to do that. If that's going to work, right? Because if I could multiply, now you can say, oh, I just multiply by 10/3, 10/3, and the 3 doesn't go away. And the reason is I can't cancel anything between the 3 and the 10 because the 3 has prime factorization 3 and the 10 has prime factorization 2 and 5. I'll never get the right numbers to cancel each other out. No matter what you pick as you build up, you end up putting a 3 on the bottom, you're going to have to put a 3 on the top. There's no way they can cancel. So the key thing is when you're looking at the number that you're going to be dividing by, and then you have to, what is its prime factors? And you look at the base you're going into, and you say, what are its prime factors? If you can't find the prime factors of the base, if it's not made up of prime factors of whatever you're going to, right? So whatever the denominator is, if that is not a prime factor of the base, it will not terminate. You can see it here. You could do that same thing, right? If you did 1, this has 2 and 5, right? 3 is a nice prime number in between. 4 doesn't work because its 4 would be 2 and 2, so it's going to terminate nicely. The next one you're going to run into will be 6. So let's say if I was doing 1/6, if I were to calculate this one out, it's 0.166, and it keeps repeating. Now, I can tell that this does keep repeating, but you can tell because if you prime factor, it's 2 and 3. And I look at the base, I'm going to 10, it has 2 and 5. One of my factors is there, but the other isn't. And that's the one that causes it to repeat. You can go down the line. Obviously, 1/7 will also keep repeating on and on and on. You can just type it in your calculator and try it out because 7 is a prime number and it's neither 2 nor 5. So you go, great, that's cute. That's base 10. Why do we care? Well, because when you go to base 2, to binary, it's even more fun because I don't have the 5. So if I'm trying to take a look at a number, let's say like 1/10. 1/10, if I'm trying to go to binary, right, base 2, right? So I want to go to some number in base 2. What's it going to look like? Well, to convert that, we can do our classic. You can either divide by 10, but to do it in binary, it's easiest to go. Right? In base 10, it's 0.1. I'm going to do my multiply by 2 trick. That's going to keep shifting it. So 2 times 0.1 gives me 0.2. 2 times 0.2 gives me 0.4. 2 times 0.4 gives me 0.8. I'm putting the radix point in just, make it a little clearer on the video. But remember, we can just ignore it also if you remember the line. 2 times 0.8 gives me 1.6. And then one more time, 2 times 0.6 gives me 1.2. And you'll notice I'm now at a 2 times 0.2. It's going to repeat this pattern. Because I've reached that same exact point on here. The next one is going to be 0.4. And then 0.8. And then it's going to be 1.6. And then 1.2. And on you go again. So this pattern here, this group of 4, is going to keep repeating. All right, so, but all I have to do is check where this is. The one after it is where the pattern starts. So, essentially, when I read this from the radix point, in binary, this would be point and then 0, 0, 0, 1, 1, 0, 0, 1, 1. And that's the part that's repeating over and over and over again. Now we knew what we do it, even though 1/10 finishes for us in base 10, of course, because well, by definition it's fine. But when I'm going to base 2, this 10 has prime factors 2 and 5, but my base 2 only has 2. I can handle this one. I cannot handle that 5. So it's just going to keep on going. And therein lies the rub. So, this just gives you another example of where those play out. So whenever you're looking at any fraction, I don't care what it is, 273 divided by 19. You can have whatever you want, right? It can be ugly. Who cares about the top? Irrelevant. You look at the bottom and you say, that bottom, what are its prime factors? In this case, well, it's 19, so 19 is a prime number. So since that's only 19, when I'm going to base 2, it only has a 2. There's no way I can handle that. So therefore, this is going to repeat. Not because anything up here, but because that. So hopefully that helps out a little bit. This is just, you can build circuits without it. The nice advantage is you can just look at a number and tell. And if it keeps on repeating forever, I really only have a certain number of digits to store. So in reality, I can't do this bar trick inside a computer. That's just human notation. The machine at a certain point is going to run out of digits, and the rest is just lost, and you get error. So this is where some of the error creeps into calculations in computers, is because they just can't represent everything. And it's kind of neat to know where that happens. So that's what this trick lets you do. I hope that helps, and I will see all of you in class. Have a good evening.